Thursday will be posted today. All right. So, and actually, after class, Alexander gave me this great link to Visual Logo, and we're going to use this link today. It's pretty awesome. They're a new version of those applets that I was trying to use last class. So if you follow that link, or if you just type into your computer visual and then go, all one word, .net, or Visual Algo. It's a visualization of algorithms, okay, that you can use to help understand some of these algorithms. Can someone get the door for me, actually, please? So when you're using this, we can take a look at bubble sort to remember how bubble sort worked. So when you're using this thing, you just hit create. When in doubt, just click all the buttons. It took me a while to figure it out. But just hit create. It shows you if you want a random array, a sorted array, or a nearly sorted. Those are our three cases. Okay. And it makes an array. I think the max was it 15 items? Yeah, 15 items, right? And then you just hit go, and it makes that array for you. Okay. And then when you hit sort, the sort button here, then you can hit go, and it'll start sorting. And there's actually a stop button here at the bottom, and you can step through your algorithm. This is what I really like. And what's nice is they show you the code, well, not code, they show you a little algorithm written out here, so it's kind of like pseudocode over here on the right. And as you step through your algorithm, as it's sorting, it steps you through this pseudocode so you can read the pseudocode at the same time that you're sorting this thing. And so it really helps us understand our bubble sort algorithm. So remember our bubble sort algorithm. We started at the beginning. I already hit play and it showed, the first step already. But we have this for loop from I equal to 1 to index of last unsorted element. Okay, so they wrote their algorithm a little bit different than we wrote ours, but it is the same algorithm. So notice that they have a for loop and they're going from so from the beginning of our array to the last sorted value, which is now none of them are sorted yet. Okay, so it'll be I to length minus 1. And notice that in this for loop, you compare each element at inner, which they call left element, to inner plus 1, which they call right element. Okay, so they're just comparing those elements to each other. If the one on the left is bigger than the one on the right, what do? You swap them. Okay, so remember that bubble sort, just like all the simple sorts, you're doing lots of comparisons and swapping. Lots of swaps. Okay, so when you step through this, remember that it compares the two adjacent items, because computer can only look at two things at once. And if the item on the left is bigger than the item on the right, then that if statement's true and it swaps them. Otherwise it's false and it moves your inner pointer down. And that's why it's called bubble sort, because when you play this thing, it looks like the bigger items are bubbling to the top. Okay. So you guys can review bubble sort more on your own. We're going to jump into selection sort. Okay, so today's topic is selection sort and insertion sort. We're going to cover selection sort first. All right. So to use this visual algo, remember you just hit create. And you guys can just follow along with me too. You don't have to use this right now, but I was just showing you how so you can do it at home. It is a really great tool. And remember that you can do random or sorted or nearly sorted. And let's see if we can figure out this algorithm. Okay. This might be a little hard to see back there, but I'll go ahead and read it to you. Okay, so here's our algorithm. It says repeat, parenthesis, number of elements minus 1 times. Okay, so notice that this is going to go through the entire array. Okay. And it says set the first unsorted element as the minimum. Okay, so that's our first step in our algorithm. And we're going to try to write this algorithm out by ourselves in a second here. So note that the first step was setting the first unsorted element as the minimum. So we know we're going to keep track of the minimum in this algorithm. Okay, so instead of doing it how bubble sort, it's a little, in fact, the code is almost like bubble sort. You'll see the code. But this time around, we're going to keep track of who the smallest value is, the minimum. For each of the unsorted elements, so that's another for loop that's going to go from the first index to the unsorted elements. So right now it'll be to length minus 1. If that element that we're at is less than our current minimum, then set the element as the new minimum. So what are we doing? We're just going through our array. We're comparing everybody to the min. And if he's the new min, we set min equal to that index. So we're finding who's the minimum in this array. Okay? And we all know the minimum algorithm, how to find a min. Okay? And then at the end of this for loop, so outside of the for loop is when we swap. This is why this algorithm's a little bit more efficient than bubble sort. We only swap 1 time outside of the loop, and it says we swap minimum with the first unsorted position. So you can kind of think how selection sort is working. He's finding the minimum and then swapping him with the guy at the end. And now the guy at the end, or actually the guy at the beginning, because we're finding minimum. You can find the max. You can do the opposite and find the max and swap them with the guy at the end. Or it's still the selection sort. Or you can find the min and then you'll swap him with your first position. And now you don't have to go through the entire array anymore. You can go the entire array minus that one that's sorted. Okay? So let's play him once just to kind of show how he works. So we're comparing everybody to min. 2 is less than min, so notice that he has the red designation now. Okay, 5 is the current min. When it compares it to 3, 3 will be our current minimum. And it swaps then 3 with the second indexed value. So you're keeping track of where you are right here also. Okay, so you're keeping track that all of these are sorted, and then you're keeping track of the current minimum so that you can swap him with this position here. Okay. So you just go through your entire array each time. I love this visualization. It's very nice. And you can see that it's comparing them. Okay. And notice that it's going to keep repeating until when? Until you've reached the end of your array. Okay. So you're keeping track of where you're currently sorted, keeping track of your current min, and then swapping him with the min. I really like that. Cool. Everybody kind of understands selection sort? All right. Let's take a look at our code and then write an algorithm out. So if we were in charge of writing this algorithm, we could write it somewhat like this. Okay, you can look at algorithms online, you can look in your book. Okay, but I do want you to write it out in your own words. So we'll write it. Well, I said selection sort we'd write together. And then you'll be in charge of insertion sort on your own. Okay, but let's look at our code and then write our algorithm also. All right, now for the code, I gave you the code from the textbook. And I conveniently put it in that zipped folder I gave you. but this is just your code from the book for selection sort. Now remember that you can open it in Eclipse, but in order to run it in Eclipse, it does have to be part of a project. Okay. So remember that if you want it part of a project, put it inside of your sorts folder with your other sorts. So then you can do your test all together. So you can right click, go to new class, and then create that selection sort class, and then we can copy and paste the code in there. I always think that's the easiest way to get it in Eclipse. Oops, dang it. So Control C, Control V, and I'll get rid of their package declaration and replace it with my own. This is what our code looks like. Remember that there are different ways to write this code, but this was your book's way of writing the code, so I just stuck with that. But if you go online, there might be a few different versions of how this code is written, but it is always the same algorithm if it's called selection sort. Maybe I'll just write the algorithm up here today. So I'm going to go ahead and write our algorithm just here in our code. And then I'll upload this. Okay, so if you guys just want to help me out with the algorithm today, I'll upload this after our algorithm that we write today. Okay. So what was our first step? And we can take a look at this code. It's kind of telling us what our first step was. And we can look at the algorithm that was written here for us also. So if we were to write out this algorithm, we could say something like, for I equal to, or we could say for I equal from the first index to the last index. Because we know that we're going to have our first for loop go through the entire array. Now this I starts out at 0 and it goes to length. If we look at our visualization algorithm here, it was the index that kept track of our sorted items. Okay, so I is keeping track of this. Notice he starts out at 0, and now he's 1. So I will be where we're going to swap that min with. I is the index where we're swapping min. You see how I is going to be that index? So notice that I is going up by 1 on every loop. Okay. All right. So for I from the first index to the last index, that was our, I guess, our step 1. I hate step numbers, but. And then what was our second step? And we can even look in the code right there. It kind of gives us a clue. We have to set our current min and our current min index. Okay. Notice that we have to keep track of both of these. We have to keep track of the value of current min so that we can compare him to the other values in the array. But we also have to keep track of which index that current min was. So that's two separate things. What index that current min is so that we can swap him, right? And then the actual value inside of the array at that index. So you have to keep track of both of those things. Okay. And we could even see that in our algorithm here. It says set the first unsorted element as the minimum. Okay. So we could say that. We could say set current min to the value at index I and current min index to the index, or to I. Actually, it's just set to I. Okay. So we're keeping track of that current min index and that current min value. And then what do we do? Looking at our algorithm, what did we do? Then we had another for loop, and in that for loop, we're checking to see if where we're at in the array, the value of where we're at in the array is less than that current min. Okay, so notice that we have to go through our entire array again. And where do we start each time in the second for loop? Where do we start our second for loop? Without even looking at the code, just thinking about it. Where do we start our second for loop? At I plus 1, right? Yeah, wherever, I is, we're going to start our second for loop at I plus 1 and go to the end of the array. Okay? And you could see that right here. Yes, we could have cheated, but it's good to think about it as you're writing these algorithms. Okay, so actually these would be sub-steps. I'm just going to leave step numbers off. And if you guys leave step numbers off, that's okay. But we should indent, right? We should at least indent. Okay, so then for, we'll say J, since they use J2, from I to the last index in the array. Okay. We want to compare. We're going to compare if the current min, which we designated up there, was the value at index I, is less than, or actually, they put, oh yeah, greater than, because we want to check if the new index of where we're looking is less than that current min. Okay, note if it's equal to it, we don't care. We want to see if it's less than it. Okay, so compare if current min is greater than where we are in the list. We could even write that out in words. Is greater, actually, let's write it a little bit different. If where we are in the list is less than current min. And yes, that's a little bit different than our code, but I think it reads better. So compare if where we are in the list, we'll say index J, we'll tell ourselves that, is less than the current min. Okay, and I wrote it different than the code. I wrote it in plain English. Remember, you can write it in pseudocode, how they wrote it too. And if it is, what do? We set current min to this value, or to the value at index J, to the value in the list at index J. And we also have to set, so we remember, because we just remember that value, we don't remember what index he's at. So we also have to set current min index to J, to where we are in the list. And I'll even call him index J, so remember that he's an index. So remember, we don't do any swaps inside of this inner for loop. This is what makes selection sort more efficient than bubble sort. We left that intensive swap operation outside of the second for loop. So we're not doing a swap on every iteration. That's what makes bubble sort so very slow. Bubble sort is the slowest of all the sorts. Okay, all the simple sorts. And it's because we're swapping. And swapping, it's an intensive operation for a computer. You have to take the ones and zeros out of that RAM location, put it in temp. Take the ones and zeros from this RAM location, put it inside of this RAM location, and then take the ones and zeros from temp into that RAM location. It's physically doing this, and it takes physical time to do a swap. Okay, so it's one of the more intensive, operations for a computer. So taking that swap out of that for loop makes selection sort more efficient than bubble sort. Okay, even though their big O times are all n squared, bubble sort is recognized as the most inefficient out of all of them. Okay. And you might see something weird in your tests, but we'll explain why. It's so weird. Okay. Well, anyways, okay. So, in writing our algorithm, notice that this is outside of that second for loop. So we'll write it out here. We'll say swap the value at index I with the value at index j. Or not j, sorry. Current min index. So you're going to swap the value at index I with the value at current min index. And you can see that down here. Okay, notice that they didn't need a temporary variable to do this swap, and why didn't they? Because they already have that current min temporary variable. Okay, and it's keeping track of that value, so that's their temp when they're doing their swap. All right. Okay, so that is our algorithm. Okay. At the end of this algorithm, your array should be sorted, which it usually is. So just comparing the selection sort to our bubble sort, just to show you that it is almost the same code. Maybe I should compare them on top of each other. Let's see if this works. So here's our selection sort. And then let's look at our bubble sort. Okay. So notice it's very similar. Okay, in the code, okay. In fact, I wish he would have wrote his bubble sort a little bit differently. But notice that it has this inner for loop the same. It has an outer for loop that goes through the entire array. Okay, it goes from 1 to list.length in your outer for loop. Here we go from 0 to list.length in our outer for loop. In our inner for loop for bubble sort, we go from 0 to length minus outer. Okay. And in our inner loop for our selection sort, we go from I to list.length. But they are going about the same, they're iterating the same amount of times. Okay, so these two for loops are iterating the same amount of times in both of these sorts. Okay. And like I said, in bubble sort, we do our swap in the loop, where selection sort only does the comparison in the loop and then saves some values, which is not that intensive of an operation. And it doesn't swap outside of the loop. But you can see that these sorting methods are very similar. Okay, the code's very similar. Okay, that's why they're usually grouped together as simple sorts. Okay. In fact, the old code I used to use from our old book, it was the same exact code, except they would have the swap outside of the loop. because you could write bubble sort a little bit differently. All right, so we got our algorithm written. Everybody understands selection sort? Is happy with selection sort? Now, if we were going to test this thing, how would we test it? Okay, so last time we tested our bubble sort. Okay, we used this performance test kind of logic where we started a timer, we did our sort, we end our timer, okay, and then we saw its time. So we wrote this testing simple sorts. Remember, I uploaded this to Blackboard too, how to test this thing, and I showed you how you can make a more efficient test with this for loop. And it tested it for 1,000 items, for 10,000 items, and for 100,000 items. And if you wanted to do it for 1,000,000 items, I say go for it. Give you extra credit. But it will take a little while to sort. You might want to sort it at night and then leave your computer running for a few hours. It does take that long. Okay? And you think how fast our computers are, 3 gigahertz, 3, billion cycles a second, and it takes hours for these things to run. It's a pretty, intensive sort. And 1,000,000 items is a lot of items. Okay? But I just made you go up to 100,000. All right. So we were testing bubble sort. So what if I wanted to test instead selection sort? I would do that same kind of tests, okay, with an array of random numbers. This was our array. This was our array printout. But if I wanted to test it with a bunch of random numbers, actually this one is not random numbers now. What is this one? This one's in reverse order. Remember that if we did array.length minus I, we did it in reverse sorted order. What if I wanted to do random numbers? Remember I showed you guys how to do random numbers. I'll show you again. You would just fill it with math.random. Remember that gives you a number between 0 and 1. 0 inclusive, 1 exclusive. So then you multiply it by your size to get a number between 0 and size. And then you take that number and you make it into an integer, not an inty, an integer. And that lops off the decimal places because we don't want to sort double numbers. And why wouldn't we want to sort double numbers? Yeah, it has decimals, and you're always told in programming books that you can't correctly check equality of double values. Okay, 1 and 2, it does take longer time to check doubles. So we just do integers. And a lot of times when we're sorting things, we're sorting them with their primary key, and a lot of times primary keys are just integers. Yes, so he should be an integer array. Yeah. So just do integers. I said double, but don't really actually make an array of doubles. I mean, I guess you could if you really wanted to, just to test it. But to turn into me, I just wanted you to test an array of integers. We kept it pretty simple. Now remember that we could take this one step further and have an array of objects. And the array of objects, the object would have to have an instance variable be its primary key in which we're sorting on. Right? Like a student ID and our employee ID, or by last name alphabetically. Okay? All right. So remember that we wrapped this whole thing up in a for loop that went from 1,000 to 10,000 to 100,000. So this for loop runs 3 times with j equal to 1,000, j equal to 10,000, and j equal to 100,000. That's why we set size equal to j at the beginning of each loop, and why we reinstantiated our array here. All right, so yeah, if we were going to test this thing, we would want to sort it right after we did our start time. And selection sort is a static method. meaning it can use no instance variables. There was no need for it to use instance variables, so it made sense that this method would be static. And since he is static, you can use his class name to call this method. Remember, that's the definition of being static. Oh, you wanted it to be a double. Oh, let's make them into integers. Let's change our selection sort so that way we can adequately compare these sorts. I forgot he was actually comparing a list of doubles. So you can easily change this guy. We'll make him an integer. Make your current min an integer as well, right here. And I think that's all we had to change in here. So just make its parameter an integer array by putting int right there. And I just grabbed these from your textbook and he had them doubles. Now, since we're going to compare selection sort to bubble sort to insertion sort, we want them all to kind of, we're trying to keep to a minimum all of the errors that we're going to have in comparing these things. Because remember that we're going to have errors because you might have other computer programs running on your computer. Remember that they take CPU time. One computer might run faster than the other computer. So we're trying to keep all of our errors to a minimum. And by having them sort an array of doubles, of course, that's going to take longer. So we'll make it an array of integers so that we can compare these guys a little bit better. Okay? So make sure to make that guy in integers. So then testing your simple sorts, he should be happy now that we're sending him an array of integers. And you should test him, of course. And then you'll record those test times, these times in milliseconds, into your spreadsheet that you had. Okay. So remember I gave you guys that spreadsheet, and you could remake that spreadsheet and have a new spreadsheet if you wanted to. Or just use this one. And you, of course, record those times right here in selection sort for random items. In fact, you could comment out and comment these back in, or think of a better way to test where you could do random items, items in order, items in reverse order. Okay. Remember, if you want them in order, I'll even label these. This one's reverse order. And then, of course, in order. You would just have it equal I. All right. But you would only want to do one of these at a time, right? Or copy and paste this loop or put it in a method. I'll let you guys make your test better. All right. Cool. Now, are those times better or worse than bubble sort? Did you guys check? So it's 4, 14, and 1278. 4, 14, and 1278. So they're as expected that they're better than bubble sort. How much better? You might think the difference between 4 and 31 milliseconds is not that great, but to a computer, this is an immense amount of time, actually. So it's actually immensely better than bubble sort. Even though they're all considered n-squared algorithms, selection sort is better than bubble sort. And this kind of pertains to what you're supposed to turn into me. You're supposed to turn in an intelligent conclusion. Remember that at the end of this assignment, the most important thing I want from you is an intelligent conclusion. Now, if you tell me that selection sort is faster than bubble sort, that's okay, but you have to tell me the why. Otherwise, it's not an intelligent conclusion. Otherwise, it's just a conclusion. I can see that it's faster. But why is it faster? Yeah, it does the swap outside of the loop. You could say, hey, swap is a time-intensive operation. Selection sort only does one swap per inner for loop, where bubble sort can do up to n swaps per inner for loop. And because it's a time-intensive operation, we can see that selection sort does run better than bubble sort. Okay, and that would be a great intelligent conclusion on that guy. Okay? So hopefully you guys all know what I'm talking about. And our directions for our simple sorts, remember that I want you guys to test all these things, how we're testing them. I call it the fun part. But remember, at the end of this assignment, the thing, you're going to get graded on the most. Yes, you conducted all the sorts, which is great. But I want you to think of why you get the results that you do. Okay, and look at the code and look at the algorithm and make those intelligent conclusions. And I just gave you one, okay, that you could write down. Okay? But make sure that you think about why you're getting the results that you are when you're writing them down. Okay, and then you're going to explain to me why we do those intelligent conclusions. I say you should make at least 5 intelligent conclusions. Okay, you can make more than 5, but you should make at least 5. There's 5 things intelligent you can say about these simple sorts. And the only thing I wanted to change in here is it says to write your intelligent conclusions on the last page of that spreadsheet, but you can make it in a separate document, okay? You can make it in Microsoft Word. You do not have to keep them in the spreadsheet. On my directions, I say to write your intelligent conclusions here. In fact, I say that you're supposed to write all the steps out here, but we haven't been writing them in here. We wrote it on a separate document. So as long as you write it in a separate document or you write it in your code, that's fine. Okay. But what needs to get turned into me is these comparisons. Okay. We wrote these 2 algorithms together, so I don't necessarily need them. I will need your insertion sort algorithm. I want you guys to write it out like how we were in class. We wrote one out today. It was pretty easy, right? So you'll be in charge of writing out this guy. And you can either write it in here or write it in a separate document. And then you're responsible for writing your conclusions either in here or in a separate document. Okay. I used to think that this was a great way, and it's okay. Depends on how much you like Excel. So that was our selection sort. Let's look at insertion sort together, and then I'm going to let you guys, you can either write your algorithm on your own or with a partner. Okay, this will be we're going to look at it together, then you guys are going to do the algorithm together, look at the code together, and then you guys can work on your tests. Okay. All right. So insertion sort is usually grouped with bubble sort and selection sort. And when we look at the code, you'll see why. The code is very similar. Okay? And they have the same running time, the big O running time of n squared. But let's look at how it differs a little bit. So remember, when you're working inside Visual Algo, you hit Create, hit Go. Then hit Sort, hit Go. I'm going to hit stop right here just to look at our algorithm that they wrote out. Their first step here said mark the first element as sorted. For each unsorted element, it says extract the element. And what do you think extract means? Take it out. Take the element out. So you're going to take the value of the element out. And for I equals last sorted index to 0. Okay. If the current sorted element is greater than the extracted element, move the sorted element to the right by 1. Otherwise, insert the extracted element. Okay, let's step through this so we can understand what that means. Okay, so right now we're at mark the first element as sorted. We extract the next element. Okay, so notice extract means we took him out. Now, do we really physically take him out of the array? No, but we copied him to another location. It's as if we extracted him. Okay? Oh, and I skipped through that, but it says if the current unsorted element was greater than the extracted element, move the sorted element to the right by 1. But he wasn't. 3 was less than 44. Okay? So what are we going to do next? We're going to extract number 38. Okay, number 38 is extracted. Okay. For I equals last sorted index to 0, oh yeah, we're in there. If the current sorted element is greater than the extracted sorted element, move the sorted element to the right by 1. Okay. What was this guy? This guy was a 38. So is the current unsorted element greater than the extracted element? Yes. So what's going to happen? He's going to move to the right by 1. Okay. Now is the current element greater than the extracted element? No. So you insert the extracted element. All right. Now we're going to take 5 and pull him out of the, extract him. Okay. We're going to compare 5 to 44. Is he bigger than 44? No. So we put him back. Actually, we put the, sorry. Yes, 44 is bigger than the 5 right here. If the current sorted element is greater than the extracted element, actually he's not greater than the extracted element. Okay. So, current sorted element is greater than the extracted element. Move sorted. Oh wait, sorry. The current sorted element is 44, and he is greater than 5. I plugged in my numbers wrong. 44 is greater than 5 is true. He moves the sorted element to the right by 1. 38 is greater than 5 is true. He's going to move to the right by 1. 3 is not greater than 5, so we insert the 5. Kind of understand why it's called insertion sort? We're inserting that element in its correct location. So now we'll extract which number? 47. We extract 47. We compare 47 to 44. 44 is not bigger than 47, so what's going to happen to 47? It's going to get put back in there. Okay, we take the 15 out. Compare 15 to 47. Of course, 47 is bigger, so he gets moved down, move down, move down, and we put 15. So notice that as we take each element, we're inserting it in the correct location of where it needs to be. Okay, this is why it's called insertion sort. Okay, you take that number out, we compare it to 47, 44, 38, and now he's inserted in the correct location. You see how this outer for loop is keeping track of this index? And the inner for loop doesn't go all the way to the end. It only goes up to the point where it needs to insert that element. Okay, it only takes the 1 off the end and then goes this way inside of your array. And actually, a lot of times this is written with a while loop instead of an inner for loop. Okay. So it takes that 26 out, moves everybody over until it gets to the correct location, and then inserts that number 26. And the insertion sort algorithm is considered the best of the simple sorts. And can you see why? It is doing a lot of swaps. Why do you think it's considered more efficient? In fact, people will actually use insertion sort more than the other two sorts. People use insertion sort in real life. Most people will not use bevel sort or selection sort, but they'll choose insertion sort and use it. And why do you think? There is a lot of swaps. You can kind of think of it, oh, maybe. And it's really good when your array is mostly sorted. So insertion sort can even go up to big O time of n if your array is mostly sorted. Okay. The reason that insertion sort's used is because of this inner for loop does not go all the way to the end each time. It's a while loop. Where the other two had to go through the entire array every single time on the outer for loop and every single time on the inner for loop. In insertion sort, a lot of times you can use a while loop even, and it only looped as far as it needed to, and then it stopped and went to the next item. And then it only looped until it needed to, it stopped, inserted that item, then goes to the next item. So it is more efficient than the other two sorts. Okay? So note that it is considered more efficient, especially for almost sorted data. Oops. So I just wanted to look at the code with you guys. You guys are going to write the algorithm, but let's look at the code. All right. So here's your insertion sort. So notice that he does use a for loop. A lot of code online will use a while loop here, but notice that this for loop has two stopping cases, so it can end early. Okay? It ends when you reach the beginning of the array, meaning you've gone all the way to the end. Or it can end early when wherever you are in the array is greater than, or it would be less than, so if wherever you are in the array, the item value of where you are in the array is less than the current element, this will be false and it'll stop. Okay, so notice that your for loop will end early if it figures out that it doesn't need to go all the way to the beginning. Okay. And then it does do the swap outside of your loop. Now they don't consider it a swap, they call it an insert. But you are saving that element, you're moving everybody over, and then you're inserting that element at the end. All right. So your next step would be to write the algorithm out in your own words for insertion sort, and you'll turn that into me. You'll add him to your testing simple sorts. You'll test him with all those three scenarios. Okay. Random, in order, and reverse order. Okay. You'll put in your times. In fact, let me put in my times and I can show you how to make a line graph out of this guy. All right. So remember that when you want to test insertion sort, you'll make him a class inside of your project, just like we did before. And you can take all of his code for insertion sort and use it. He's a static method as well, so you can just use the class name to call it. So if I wanted to test insertion sort, and he does actually use a double list, right? So we'll have to make that into an integer list so that we can properly compare these guys. Okay, and we'll have to make this guy an integer. So make your current element an integer and your array an integer array. I changed the wrong one. No. Oh, it's named array. That was his default name, was list. All right. And so then if I test this guy with random numbers, it was 3 milliseconds. Remember that you can run this a couple times to kind of get an idea of how long it takes. But 3:30 and 8:78. And you can see in these times right away that he is the more efficient sort. Okay. Now to make a graph out of this guy, it's actually pretty easy to do in Excel. I do want you to make a little line chart, or visual people, it's good to make line charts. Just to practice making line charts. I just select the whole table, go to Insert. You can even go to recommended charts if you wanted to, but you do want the line chart. I actually did not recommend a line chart to me. And I remember last time Excel did not like our data. And I don't think he likes him again. He graphs him wrong, I think. So if he's going to graph him wrong, damn it. I was hoping that they would fix that bug by now. So he does it fine for 2 elements. I remember last time we had a problem. And it was funny, is the old version of Excel used to do this no problem. And then when we updated our Excel, sometimes he has problems with 3 elements. And notice that he is graphing the, oh, I guess, oh wait. You're going to switch column. Oh, there we go. Actually, he did it okay. Did you guys see what I did? So first I selected everything. I even selected the headers. And then I went to Insert, and I went to that line chart. Okay. But then I noticed down here, I finally noticed that my legend, okay, was showing my 1,000, 10,000, 100,000, and this is still kind of okay. But if you open up your chart tools in your design, you can switch the row and column. A lot of times I tell people just to push that button if what you're getting is not right. And let's see if this looks correct. But when I switched my row and column, he seemed to come out a little bit better. And that does seem about right, because my bubble sort did take immensely longer than my other 2 sorts. We almost have to go to 1,000,000 items to start to see their n squared. But I say make a chart anyway. So make this little line graph here. And charts are really easy. Okay, remember that you can click on designs and different things. All right, so I think I'm just going to let you guys work to the end of the period here. I can come around and check out your tests or your intelligent conclusions if you'd like me to. And you can work together with somebody, but remember that you want to turn in your own work at the end. So I don't mind if you guys collaborate on this. Okay, if we compare results, it's excellent if you guys work together and compare your results to somebody else. You can even discuss what to write for the intelligent conclusions together. Okay, that would be great. But just remember to turn in your own work and not just copy paste somebody. Okay? All right, so good place to stop.